the session again. Okay. So I think we can start. Yeah. So welcome to this first lesson of the optimization modeling course. I guess you know who I am. If you don't know, I am Alberto from module 2.2, and I'm also helping the cluster 2 coordination. And I'm doing that because if you remember, there was some interest after the survey on the winter school about learning more about optimization. And in these like 3 lectures, I will share with you something about basically linear and integer programming using AMPL, that is the software we choose for modeling. A few informations before starting. Number 1, as you know, there are 3 lectures, right? So one is today, one is in 2 days, and then next week we have the last one. You should have already installed AMPL and Cplex, and it should be working on your laptop, I hope. The way this course is structured is that the first part, let's say the first hour, more or less, is learning, and then we have a pause of around 10 minutes. And then the second part will be focusing on practicing. Okay, so we will do some activities together, and then I will split people in breakout rooms where you will have to work on some problems yourself. And then we come back to the general room where we can go through the solution of these activities, and then we can discuss. You know that there is a website of the course I shared before, like here you have the link. I will be uploading these slides later. So the idea is that I don't put the slides before, not because I am mean or I don't want to give you the material, but because in my experience, if you follow without having the slides, the attention is level is higher. Of course, if you need help at some point during the course, you can send me an email that is here. Another thing I want to tell you is this: for this course, people belongs to houses in a kind of Harry Potter fashion, if you want. So what is the idea? There are 4 groups, 4 houses, and people will belong to one of them. You don't know which one. You will know only later. The idea is that eventually there will be 2 homeworks to be submitted for after lesson 2 and 3. And there will be some grade, okay? Now, at the end, to identify the, let's say, the ranking, or because there may be some small prize according to the ranking, of course, I will have to consider the score of people in the same group. But what I wanted to avoid is the situation where if you know your group, sometimes there is someone who is doing more than others. So this way, you don't know the group you belong to, so you don't know who are the other members. And you will only know at the end. I think it's a little more interesting this way. Also, during the practice session, I mentioned that people will work in groups when I split in the breakout, but it will not be the same group as here. It will be just random mixing. Okay, so if later you will be with other 3, 4 people, it doesn't mean that it's the same people in your house. Okay. Homework we will discuss later, but for this lecture there is no homework. Yes. Is there anyone? I heard something. No. Okay. Good. So before starting, just a quick introduction about optimization, right? So I didn't know optimization before going to university, and then I remember the first course I got was called Operations Research 1. And what I like about that is the example that my professor used to introduce the field. And the example was quite interesting. It was something like, imagine you have $100, okay? 100 euros in Italy, but let's say dollars. And then the question was, if you can go and change your 100 euros to, let's say, another currency, maybe you go from euro to Singapore dollar to US dollar to whatever, and then you come back to the same currency. If there is a way by going through some set of changes that you can have more than before. So maybe you start with $100, you end up with 100.5, even a small increase. Basically, you find a way to make money from nothing. Now, this is not possible anymore because before you get excited. But what I like about that was, number one, understanding that this stuff can be applied really to any field. It can be finance, it can be transportation, it can be power system, it can be really anything. And the second one is that when you think about a problem like the change currency, right? The number of possibilities can be really, really huge. However, you just need to focus on how to model the problem, not really on how to solve it. That is something I really like, because if you start to think at how to design a way to solve the problem, yes, some branch of optimization is doing that as well. But what we focus on this course that is called mathematical programming is really the part of optimization focusing on creating a model of the problem and then using software that is already there to solve the problem. So we don't focus on solving, but on modeling. That's why even very complex stuff can be modeled, and then we don't care about how to solve them to some extent, okay? So I mentioned mathematical programming. What is mathematical programming? Well, mathematical programming is this branch of optimization, as I said, focusing on finding the best solution, or often we will say the optimal solution of your problem. And first thing is, okay, how do you define what a possible solution is? So in mathematical programming, usually a solution is considered to be feasible if it respects some constraints. So we imagine you have a set of constraints telling you what you can or cannot do. If you have a budget of $100 to buy your food, you can spend up to $100. If you want to buy something that is costing $150, is infeasible, okay? So we have the constraints that are telling us what we can or cannot choose. Then, okay, out of all the possible solutions, the feasible solutions, we need to find the best one, right? The first point. Now, when I say best, it means that we need to have some way to tell what is the quality of one solution versus another one. And this is given by the objective function. So you can think of the objective function as a kind of performance measure where for each solution, there will be a score associated with the solution. And this function can be something you want to maximize or minimize. So for example, imagine you are running a company and you want to maximize your profit. Well, if you have two decisions to make, right? You have to decide to go option A or option B. What you do, you look at the revenue with option A, revenue with option B. If option A provides larger revenue, then you choose that one, is the best solution. And then, of course, we need to have the variables. So what are the decisions that we can make? Okay, so these are basically the main elements of a mathematical programming problem. I repeat, you have a set of constraints telling what you can or cannot choose. And the choices are the variables. Objective function is what is telling you. It's basically a way to compare different solutions to understand what is the best one. And you want to find out of all the feasible solutions, the best one for your problem. This is more or less what we want to do. A few examples that you may be familiar with. Let's say you're driving, you use your navigator, you want to go from point A to point B, and you want to look for the shortest path. Well, this is an optimization problem because the shortest path is basically the objective. You want to minimize the total length, right? So when you have different options going from A to B, how do you choose the best one? Well, is the one with the minimum length, right? And the choices can be the routes that you are taking. Another one could be, what is the best building design for maximizing energy efficiency? Maybe some people is working on this topic. Finance, right? How to build a portfolio to minimize risk and achieve some expected return. Diet problem, this I will show you later, okay? So if we look at mathematical programming, usually it goes this way. We have, first thing to do is we need to formalize the real world problem, because we have a problem we have to solve and we need to make it formal. Usually it means we need to make some assumption to simplify, to really understand what we want to solve, right? And when we have this formalization, then we need to create an abstract mathematical programming model to describe the problem. So first we understand the problem, then we need to basically write a model with some software that in our case is AMPL, describing the problem. Then when we have that, we need to solve the problem, right? So we give this model we have just created as an input to a solver, and we hope to get as an output the optimal solution for our problem. And then the last step is we have to interpret the solution according to the real world, because maybe we made some simplification, maybe we made some assumptions. So the number we get from the solver needs to be somehow interpreted and translated back into the real world application that we were studying. So this is more or less the picture showing the procedure. And in this course, we focus on point 2 and 3. So point 2, that is basically transforming the abstract model into an AMPL file, that is the software we are using, and then how to solve the problem to get a number, to get the solution. Because I believe for you guys, the most interesting part is really to know how to solve in practice the problem. Because you are working on very different fields, but sometimes it's very likely actually that you will find during your research some optimization problems. So knowing how to solve it in practice, I think is what is really important. Okay, how do we create the model? As I said, in this course, we will be using the language AMPL, that means a mathematical programming language, no surprise, but there are other software. One is Pyomo, is a package for Python, there is GAMS, there are others. So it's not the only one. And what about solving the problem? Okay, for solving the problem, there is already a wide range of software that you can use. There is Cplex that we are using in this course. Cplex is the state-of-the-art for linear and integer problems. We have Gurobi that is also good for integer and linear problems. We have stuff for non-linear, non-convex. It really depends on the kind of problem we have to solve, okay? So imagine this. You model the problem, you understand which kind of problem you are dealing with. We will come back to that later. And when you know the specific type of problem, it can be integer, linear, non-linear, whatever, then you will know what is the most appropriate solver to use. Okay? So as I say in this course, we practice modeling with AMPL. And why do I think this is important? Because there is not only a way to model a problem. You see, you can have a problem and then you can create different models that give you the same solution. But different models can have a huge impact on the resolution time. Because maybe you can put some kind of, I don't know, constraints, or you can find a way to reduce the number of variables. So if you play with the model, you may be able to really save a lot of time by solving the same problem. Okay, let's start with the scary stuff here. You see this is the way that usually a mathematical programming model is presented, okay? So let's go through the elements one by one. In this case, we have the first one is we want to minimize a function f of x. It can be also maximized. This is the objective function I mentioned earlier, okay? So ST means subject to. So when you see ST, then you see usually a list of constraints. The constraints can have a different form. They can be equality. They can be less than or equal to or greater than or equal to. So here, for example, you have a function g of x less than or equal to 0. H of x is equal to 0. But all these are more or less interchangeable, okay? One point I want to make, you don't have strict inequality here. because if you had, the problem would be not well defined. Because, quick example, if I ask you what is, I want to maximize, I don't know, X, and X is less than or equal to 10, then of course the optimal solution is 10, right? But if I ask you what is the max of X if X is strictly smaller than 10, then what is 9.99999 is never a number, right? So because of this problem that is, I mean, I don't want to go into the theory, but this is just for you to understand why we usually have inequalities that are not strict. If you really want in your real world problem to guarantee strict inequality, usually we put some epsilon, but we can discuss about that later. Then we have variables. So X is a vector of variable. So what we have to choose, basically the value of X will be only known after we solve the problem. And then they can be greater than or equal to 0. Usually they, like, this is the standard way to represent a problem, but of course they can be less than or equal to 0, integer, whatever. So when we see this kind of formulation, you should read it this way. What is the solution X star? When you see star, usually it means the optimal solution, the one we know after solving the problem. So what is the value of the variables such that all the constraints are respected, so the solution is feasible, and it also produces the best value of the objective function f. Okay, so this is more or less the kind of problem we are dealing with in this course. If you have any questions at some point, just let me know, okay? I should be able to see the chat, yeah, or you just stop it. Okay, I say before that when we have to solve the problem, we need to choose a solver. And when we choose the solver, we need to know the class, the kind of problem that we are solving. So the most, let's say, common classes are those, but there is more. But let's start with the linear programming. So when you are solving a linear program, it means that all the functions you see here are linear. So f of x, g of x, you don't see any kind of square or crazy expression, or they are just linear function on x. Then you may have integer linear programming. So it's like before, but some or all variables are integer. So if you have all variables integer, usually it's called integer linear programming. If there is a mix, some are integer, some are not, then is mixed integer linear programming, or MILP. So we stop at these two in this course, okay? But just for you to know, there is more. There are non-linear problems. So it means some of the functions are non-linear. You may start to see things like square, cube. You may start to see products between variables. You may have other things like sometimes log, exponential. So something that makes the problem non-linear. And then to make things worse, when you put on top of that integer variable, then you have the so-called MINLP. So MINLP is the one of the hardest to solve because on top of having the complexity of integer variables, you also have the non-linearities. There are also different categories for these problems. So some people look at the convex versus non-convex. You can have a robust or stochastic when you deal with uncertainty, black box, and so on. But for this course, again, we will focus on linear and mixed integer linear programming. Okay. So as I say, we have different solvers, and the solvers take as an input the model that you created, for example, with AMPL, and they try to give you back the optimal solution. As I also mentioned, we use Cplex, that is one of the best solvers for linear and mixed integer linear programming. Okay, so that's why we have the setting AMPL as a language to model plus Cplex to solve the problem. Okay, let's go through now the basic use of AMPL, the main syntax command. But before moving to that, do you have any question? No? Okay, so we can proceed. AMPL, as I said, is a mathematical programming language. What is very interesting here is that the way you model with AMPL is really close to the mathematical form, so to the way you will write the model on the paper. Okay, that's why it's quite useful, and also is quite easy to use. Of course, there are all the things that you can expect in a language. There are some keywords that you need to use to specify different things. If you want more info, you can go here. There is a book with all the information on AMPL. I put the link, I think, on the website of the course, right? And you can just have a look if you want to know more. Okay, so when you work with AMPL, there are different ways to create a model, but the one that I want to focus on here is this one. Separate a problem in three parts. One is a model .mod file. Here we specify objective, variables, constraint. Then there is a data file that can be optional. And then there is a run file. A run file is basically where we say, we specify the solver we want to use, the kind of output we want to be displayed, and so on. So why did I say data file is optional? Because the data, so the numbers of your problem, they can also be directly included in the mod file. Okay. So why then there is this option? Because sometimes when you have to solve problems, you may have the same problem with different input data. So instead of writing a different mod file for the different input, you just write the mod file once, and all your different instances will just be different data file. So you create one time the model, and then when you want to change data, you just change this file rather than replicating the same model every time. So that's why you have also the option of a separate data file. But we will be using both of them, so you will experience both ways. Okay, let's start with the stuff now. How do we declare variables? Okay, so you saw in one of the previous slides that one of the key components of an optimization problem is variables. So to declare a variable, you use the keyword var. Okay, so var, then you write the name of the variable. It can be anything. And then you can directly specify the bound. So for example, if you know that this guy x1 is greater than or equal to 0, then you will call it this way, var x1 greater than or equal to 0. And then you always end with a semicolon at the end. Okay. What about declaring parameters? And when I say parameters here, I really mean data. Okay. Well, okay, you are already at the advanced level. Okay, if you want to have matrix variable, I will show you later how you can do that. We need to use sets. Okay, but it can be done. You can have variable with different indices, even more than 2. Right? You can have variable x, I, j, k, whatever you want. But for now, let's just start with the simple one. Later, you will see also how to index variables. And the same can be done for parameters and other stuff. So parameters here, as I say, is data. This way, we use the keyword param. So I define here a parameter A, and I can also specify a default value. Why I do that? Because as I said, I can put value in the data file, but I can also assign a value directly here. Default tree means if you don't find any definition, like any value for A in the data file, you just use 3. If there is a data file with another value, that you use that value. Okay, this is the meaning of default tree. Then we have the objective function. Okay, how does it work? So the keyword is minimize or maximize, depending on your problem. Then you put a name of the function. In this case, is fun, but it can be anything. Then you have to use this syntax here, followed by the expression. So this expression is A times the variable x1 that we declare here, minus 2 times the variable x2. Always end with a semicolon. Multiplication, you need to put the star. And you see here that we use the parameter A that is defined here. So we could have written 3x1, right? But imagine that this parameter changes for different instances. then it's better to indicate it as A, and then every time we have a different instance, we have a different data file with a different number for A. But more or less, this is the idea, right? Variables are declared like that, parameter and objective function. What is missing? Constraint. So remember, I told you there is this ST in the constraint that means subject to. Well, here you do exactly the same. You have to write subject to, name of the constraint, and then here you write the constraint. So in this case, this problem is we want to minimize the function 3x1 minus 2x2, where x1 and x2 are greater than or equal to 0, and x1 plus x2 must be equal to 4. This is the kind of problem we are solving here, okay? Now, this is something I already said, the fact that we can assign the value of the parameter A in a data file, and then we can basically indicate a different value that rather than the default value in the mod file. Now, what about the run file? Well, in the run file, we need to specify a few things. We need to tell first what is the model. Let's say that this model that we just created is called example.mod. So we need to say, okay, the model is this. The data file, if we have something, we write data and then the like example.dat if we have, but in this case we don't. We need to tell what is the solver. So in this case, we are using simplex. So this is the syntax, right? Option solver, and then you put the name of the solver. You may also specify here some kind of settings for the solver, but we just use the default for now. Then the keyword solve means solve the problem. So find the value of the variables that optimize the objective function, and then we can show the values with the command display. Okay. So the summary for all these, and don't worry, I know it's a lot of stuff the first time, but by practicing, it will become very clear. And then later you will also have the slides to refer to. So each variable is defined with a var statement, okay? Objective function, you need to say minimize, maximize, followed by the name, and then you write the expression. For the constraints, the keyword is subject to. Remember that multiplication is the star. So if you write 2x1, it doesn't work. You need to write 2 times x1. If you have the greater than or equal to, you write it like this. So greater followed by equal, similar for less than or equal to. This one does not really apply here because we are just using simplex, and display we show the optimal variables. Okay. Okay, so let's go through the first complete example, right? So you will have a sense of how it works. Remember that, okay, I show you the general expression for a mathematical programming model. When you have a linear programming, LP, usually is written like that. So remember, because everything is linear, the objective function is just a multiplication between some parameters and the variable, like 3x1 minus 2x2. And this form, where A is a matrix, is usually a way to specify a set of linear inequalities. Okay, so this is just, I mean, I don't really want to scare you with this, but if you see something like that somewhere, then you know that is usually referring to a linear programming problem. Is the standard notation C transpose X subject to AX equal to, or greater than or equal to B sometimes. So in our case, what is the problem we want to solve is this one. Remember, we want to minimize, if you see here, this was the function ax1 minus 2x2, but a is equal to 3. So we want to minimize 3x1 minus 2x2. The constraint was x1 plus x2 equal to 4. And then we have two variables greater than or equal to 0. So this guy here is the problem we want to model. So let's see how this will look like in AMPL. Okay. So this is the mod file. Remember, the mod file is where we write the variables when we have the constraint objective function, and we may have also the values of the parameters. If we don't have them here, we have them in the data file. So Okay, so even if you don't specify the numbers here, you still need to, you still need to declare the parameter, because the model need to know that there is a parameter, right? The value may be specified later, but at this stage, when you write the model, you need to specify that there is a parameter. So let's say there is a parameter n, that is the number of variables. So we have two variables, right? X1 and X2. So n is equal to 2 later. Then we define a set. What is a set? Someone was asking earlier, how can we define variables like a matrix form? This is more or less the idea. Sometimes, if you have just two variables, you can just write X1 and X2. But what if you have 100 variables? You cannot possibly write X1, X2, X3, X4. Come on, right? So what do? If you have many variables, you specify a set. Imagine n is equal to 100. This thing here, 1.n, means generate all the numbers integer from 1 to n. So this set will be the set including number 1, 2, 3, 4, 5 up to n. Okay. Then when you write something like this, variable x of n, it means that you will have one variable for each element of this set. In other words, if this n is equal to 100, this set here is all the numbers 1 to 100. And this means that you have 100 variables, x1, x2, x3, x4, up to x100. Okay? So this is the thing, right? And if someone was asking about the metrics, well, you can specify two indices like n and m. Then you have x12, x13, x31, whatever you want. But let's start with like a simpler way, right? So remember, in our case, n is equal to 2. This set is the set of indices 1 and 2. Then we have a parameter c that in this syntax is basically including the numbers 3 and 2, right? Because when we have c transpose x, it means we multiply a vector 3, 2 by variable x1, x2. We have a parameter a of n. They are the coefficient of the constraint, and then a parameter b that is 4. So again, we can just write all the numbers here, but I want to show you how to use the data file. So here we define the variable x of n greater than or equal to 0, meaning x1 and x2 are greater than or equal to 0. And now look at the objective function. Why did we have all this trouble of defining set? Because look at how easy it is now to write the objective function. Instead of having to write all this expression, that in this case is short, but it can be much longer, we just need to write something like that. You sum for each element j. Here you can write anything, I, j, k, whatever you want. But the idea here is for each element j in the set n, and the set n is 1, 2, the objective function is c of j times x of j. So c1 x1 plus c2 x2, where c1 is 3 and c2 is minus 2. So you see that we are writing exactly this. If you are familiar with Excel, I think there is something similar called sumprod, is a function in Excel. But basically, this will allow you to save a lot of time when you write long expressions. And then the constraint, same thing, right? We want to have, as I say, a is 1, 1, the coefficient of x1 and x2. So we can write x1 plus x2 equal to 4, but we can also write something like that. And b is equal to 4. Okay, so this is more or less the model. I know it may be a little complex, but don't worry, really trust me. You just need to practice. After a few models, it will be much clearer. So just some comments here. As I say, the sets parameters, everything must be declared before they are used. Okay. Okay, this is about statements. Fine, you can split. Okay. What is interesting is this expression, right? Cj, where you have the sum over j, you will have the objective function as I showed you before. And then in and sum, yeah, they are other two keywords. Sum is the sum, and in you are basically saying that J is, you are summing for J in this set. So if you do the, I don't know if I can write here. Do they have a, maybe with this, let me see. Just want to show you something. Oh, okay. So when you have sum, the sum of J in N, oh God. Sorry, first time I use this tool. When you have these, oh, don't see my mouse now. Okay. So when you have J in N, this is equal to the sum of J in N. So when you see this expression in AMPL is mathematically equal to this. Okay. Okay, now I have to erase everything. Okay. So data file where we specify the numbers. As you remember here, we have some parameters N, C, A, and B. We didn't specify the values. We specify them here. And I don't know if, yeah, M actually is a mistake. It should not be there. N, C, A, and B. So when you have a single number, you just write like that. When you have a set, for example, C, where you have C1 and C2, this is the syntax. You write the index here and the value here. Also, the parameter A, we have A1, A2. So A1 is equal to 1, A2 is equal to 1, and the parameter B is equal to 4. Okay? Now, about the data file, this is something I already said, that basically we can use a model to specify just the structure of the optimization problem. And then when we want to solve a specific instance, we can just create a data file. So we don't have to replicate the model every time. We just need to write the model once. Last piece, run file. In the run file, we have to say, well, model is this, and you write the name of the model, data, and then you write the name of the data file. You specify the solver you use, right? Like this is the syntax I use. The syntax that you can use for the demo version is the one that you have seen here. This one, right? Solve means solve the problem and then show the variables. So what happens when we solve this problem, right? You see this is the output. Cplex, blah, blah, blah. Optimal solution objective is -8. And then because we display the value of X, this is the value of the variables. X1 equal to 0, X2 equal to 4. Okay. So if you go back to your model, to your problem, you want to minimize this. The solution is to put 0 to this, right? And 4 to this. And you minimize because you get -8. This is the minimum value you can get with this problem. So this is more or less what happens. Okay. First, you create the model file. Then you create the data file if you need. Then you create the run file where you specify what is the model, what is the data, what is the solver, solve and show me the solution. You run the run file and then you get the output. So under Windows, it may be a little different sometimes because I'm using Mac. So if you are under Windows, you may need to double click. There is an AMPL application in your installation folder. And then when you have shell, you write include example.run and you press enter. Okay, so if you are under Windows, you may have to do that. Under Mac, I just need to write something like that. This command, AMPL, then this symbol, and then the name of the run file. Okay. Okay, so this is the more or less the basic functioning of AMPL. Is there any questions so far? No? Okay, So before moving to the next part, I want to show you the, oh, there is one. Wait. Yeah, you can also mention the path of the solver. Like when I saw this, I assume that everything is in the same folder. So just to make it simple, you put all your mod run data file and the Cplex in the same solver folder. If you have stuff in a different path, you can. If you want to make it even easier, you can, if you know how to deal with the variable like the environment variable of Windows, you can change them. So anytime you write AMPL and Cplex, it will work. But yeah, you can specify the path. So just quickly, the diet problem is an example I want to, okay, wait, yeah, no problem. This is a very classical optimization problem, is very old. And the idea was that you have to find a minimal cost diet that satisfies some nutritional requirement. So basically imagine that you have some food, right? And different food, they have different amount of vitamin, okay? And they have different cost. So the question is, what is the choice of foods that cost the minimum possible but satisfy all the requirement of vitamin, for example? And this is motivated by, okay, originally the desire of the army to find blah, blah, blah. Many problems in operation research, we realize, started from problems from the army. So it's no surprise. And there was a solution, like we can go through this if you are interested. So someone found a solution with this cost, and then later when they showed the optimal solution, it was really close to that, like 24 cents more only. But what is important for us is, well, the LP formulation, as I said, what we are looking at is the amount of food we buy. This is the variable. So we have different kind of food. We need to decide how much to buy. We want to minimize the total cost. So you can imagine that the vector C represents the cost of each food. The matrix A, so these constraints are those telling us the requirement. Like I need to have at least this amount of vitamin A, B, C, blah, blah, blah. And the vector B is specifying these values. What is the minimum we need for the vitamin? So in the original problem, we have 77 food items and 9 nutrients, but it's too much. So we just look at a shorter version, okay? So we just consider we have bread, beef, and fruit. And we assume that 1 unit of bread costs $1, 1 beef 6, and 1 fruit 0.6. Okay, so these are the costs that you should start already to realize. This goes to the objective function. Then we know this. We know that if we have 1 unit of bread, we have 3 units of vitamin A, 0 vitamin B, and 1 of proteins. If we have 1 unit of beef, we have 2 units of vitamin A, 1 vitamin B, and 6 protein. And then 1 unit of fruit, we have 0 protein, 4 vitamin B, and 5 vitamin A. So all these things are part of the constraints. And then what we need is to find the amount of food by minimizing the total cost, such that we can guarantee to have at least 30 units of vitamin A, 15 vitamin B, and 25 protein. Okay? This is more or less the diet problem. So we need to write the AMPL. Remember, we need to write the mod file, data file, and run file. Let's start with the mod file. So in the mod file, remember, we have variables, constraints, objective, and then we have to set the data, the parameters, and the sets. So what are the sets? Well, we probably, as variable, we need to decide the quantity for each food, right? So we need to have a set of foods. The foods are bread, beef, and fruit. Then we have a set of nutrients. So we have vitamin A, B, and proteins. So these are our sets. And then the variable is 1 variable for each food. So eventually we have to decide how many units of bread, how many units of beef, and how many units of fruit. So you see now why sets are interesting, because instead of writing X bread, X beef, X fruit, this way we can save time. It's the same as X1, 2, 3. But we can also have names to index this. It's okay. What about the parameters? So for each food, we have cost. So we have a parameter cost, and this means, if you remember, for each element in food, we have the cost, we have the amount. So this is the metric say. This is telling how many units of nutrients for each food. Okay, and then we have the parameter B, so the right-hand side of the constraints, what is the minimum requirement for each nutrient. Objective function, we minimize what? The sum J in food cost times X. You see, this is pretty standard. So for each unit of food, we know the cost. So when we sum over J, the cost times the unit of food, we have the total cost, and we want to minimize that. This constraint is what? Okay, this is interesting. So when you see a constraint and then you see something like that, right? It means that you have one constraint for each element of the set. So instead of writing one constraint for each element, you can just write one expression only. This means subject to mean like the name of the constraint. But when you see this, it means you have multiple constraints, one for each element in this set. So for each nutrient, we have what? That the sum J in food, so the sum of each food, of the amount of the nutrient for in the food times the food is greater than or equal to the minimum. This means for vitamin A, we look at how many items of food. We know how many items of vitamin A for each of these food. The sum, so the total vitamin A of our diet is greater than or equal to the minimum required. And then we do the same for vitamin B. So it's another element of this. And then for proteins. Okay. So if we want to write the mod file, this is how it looks. When you see this, hashtag is a comment. Okay. So we have the two sets. We have the parameter cost, the amount of nutrients for each food, and the minimum value of the nutrients we need. We have the variables. We want to minimize the total cost subject to this condition that for each nutrient, we can guarantee that we have at least the minimum. Data file. Well, the set foods, as I said, is the three foods. Nutrients is the three nutrients. So in the data file, you can specify the sets as well. Parameter cost, remember, as I said, we write when we have a list. The first element is the index 1, 2, 3, or bread, beef, fruit, and then we have the value. So the cost of bread is 1, the cost of beef is 6, fruit is 0.6. This is the way we specify a table, data table, okay? So we write the name of the parameter that was amount. Then here we write the three, like the names of the rows, and here the names of the columns, and here the numbers. So here it means that 1 unit of bread will have 3 units of vitamin A. 1 unit of bread will have 0 units of vitamin B. It's like a matrix kind of form. And then the minimum requirement for vitamin A, we need 30 units, 15 for B, and 25 for proteins. Around file, as before, we put what is the mod file, data file, solver to use, solve, and display X. And when we run it this way, or the other way I explained with Windows, what you get is this. You will get that the total cost is 26.69 something, and these are the optimal amount of food that you have to buy. So 3.69 units of beef, 2.83 units of bread, and 2.82 units of fruit. Okay, so when you buy these, you minimize the cost, and you can guarantee that you have these, the requirement of 30 units of vitamin A, 15 of vitamin B, and 25 of proteins. Okay. Now, you may be wondering, okay, but these are units of beef, bread, and fruit. Maybe it makes more sense to have integer value. That this is basically the topic of the next lecture, that is integer programming. So before going to the next one, I think we can take, let me see what is the time now. It's 10:20, right? Around. So maybe we can have, I don't know, 5 minutes pause around, or maybe let's come back at 10:25. Okay. And then we can start with the second part. Okay. So see you in a while. And if you have questions, just write on the chat. I can, or you can ask.
I think my time is 11 o'clock right now.
Oh yeah, sorry, not 10. 11, yeah. I have my phone is. So what time is it now? Do
11.
Now is 11.
Right.
Oh, then if it's 11, then we can come back at 11:10. So my phone is wrong. Okay. If it's 11, then we can come back at 11:10. Okay. 11:10.
All right. Thank you.
Yeah. Thank you. Okay, so now what we are going to do in this second hour is the following. First of all, we are working together on a problem, and then I will split people in breakout rooms, and then you will work on some questions, follow-up questions for that problem yourself. Now, to do that, two things you need to have. First one is to have AMPL and Cplex running. I hope you have. The second one is you need to have downloaded the files that I uploaded on the website of the course, and I sent a mail about that. Because in that zip file, you will have the material to work on the problems, okay? The problem we are working on now is a very simple problem about investing. So this is the scenario. Imagine there are two funds, X and Y. And then you know the return of the fund X, that is 4.5% a year, let's say, and that of fund Y is 5% a year. And you have 50,000 K, 50K actually. What you want to do is this: write an optimization problem with AMPL and solve it. So the way you have seen earlier, to find the allocation of your 50K to fund X and Y, in order to maximize the total profit. Of course, this is a very simplified problem because there are many things missing, but it's just for practicing using AMPL. Okay. Now, let's try to understand the problem according to what we have discussed so far. What is the file, the data file? Well, we need to look at the parameters of the problem, so the data. The data, the numbers we have seen here in the description are three. The return of the fund X is 4.5%. That of fund Y is 5%. And then the total capital we have, the 50K. What about the objective? Well, we want to maximize the total profit of the portfolio or total return. What are the variables? Well, we need to decide how much money to allocate to fund X and to fund Y. And what is the constraint? In this case, there is one constraint only. Well, the total amount of money invested is 50,000. So now that we have understood that, this is remember the first, one of the first slides I was mentioning, there are 4 steps. The first one is to starting from a description of the problem, that is this, to a model. And the really first step is to identify parameters, objective, variables, and constraints. So that's what we do at the beginning. From a description of the problem that can be written or someone explaining to you the problem, we need to understand what is the objective, what are the variables, what are parameters, and what are the constraints. And just to share with you, in my experience, many people at the beginning confuse parameters with variables. The easy way to understand the difference, the parameters are basically the numbers you know before solving the problem. The variables are those you know only after solving the problem. Okay? So if there is any confusion, just remember that. Now that we have that, we need to write the, remember, mod, data, and run file. So we have the parameters, as we said, return of the fund X, I call it Rx, okay? And the return of the fund Y, I call it RY. And then the capital, that is 50K. Then we have two variables, X and Y. And these variables represent the amount of money invested in fund X and fund Y. And these variables are greater than or equal to 0, because we are not doing short selling or other things. So, you have to invest a positive sum. What is the objective we want to maximize? Well, I call it OBJF, but you can call it as you want, really. These names, all the names actually, if you don't use keywords, is fine. So maximize objective. Okay, in this case, what I did is if we have a return of 5%, the parameter I brought 5. I could have written 0.05, but I just divide by 100 in the objective, is the same. So the objective is the fund X times the return, right, is the return from the fund X. So if I put 10,000 here and I know I get 5%, then I do 5% times 10,000, and this is what I gain. So the total return of the portfolio is how much we put in fund X times the return of the fund X plus how much we put on the fund Y times the return of the fund Y. And remember, there is a constraint that is saying we have to use $50,000. So X plus Y is equal to the capital. Is it okay so far? So this is really the first step when we translate a problem into a model. What about the data? Well, we have Rx, the return of fund X, is equal to 4.5, RY 5, and capital 50,000. So this is the data file. Now, again, I could have written here 0.05 or 0.045 and not having had the 100 here is exactly the same, okay? I could even have written the value of the parameters here, like param Rx default 4.5. Remember, we have seen the default before. Param RY default 5 and param capital default 50,000. This way, we don't even need to use the data file. But just for practicing, I want to show you also how to do it with the data file that may be more relevant when you are solving larger problems or problems where you have to try with different input. Finally, the run file. So model is a keyword, again, model, and then we write the model name. I call it funds.mod. So this is funds.mod, right? This is funds.dat. So now we tell to the solver that, okay, the model is funds.mod, the data is funds.dat. The solver we want to use is simplex. So you write the path, whatever it is. Solve means solve. And then we want to see the values of X and Y. If, as I said, we put these values directly here, then of course we can remove this line, data funds.dat. So what happens when we solve the problem? Well, you find the solution. The objective is 2,500, and the allocation is to put 50K on fund Y. Does it make sense? Let's see. Well, of course, because we want to maximize the total return, the objective is to put everything in the fund that is giving you the largest return. That is the fund Y with a return of 5%. So if we put 50,000 on a 5% return, what do we get? 2,500. That is objective. That is the objective value. So it makes sense. Is what we would have expected. Many times when we solve optimization problems that are much harder, it's very, very difficult to see so clearly if the solution makes sense, right? But in this case, because the problem is simple, you can double check and see, hey, the solution is actually what I would have expected. Of course, if we have additional constraints, this may not be the solution we find. So what happens now? you will have to solve these two problems. Okay, starting from this, from the data, mod data and run file that you can download from the website. You have two questions. Number one is, imagine that now there is a new constraint on the problem. And the new constraint is that you cannot invest in fund Y more than twice of what is invested in fund X. Now, I want to know what is the return if you solve the problem that you've seen before with this additional constraint. So what do you have to do? You have to specify in the model file another subject to, another constraint like that, that is representing this condition. And this is the first problem. The second problem, now the setting is a little different. We don't have the fund Y anymore. Okay, we know that 50% of the capital is allocated to fund X. So the 25,000 are on fund X. And 50% is in another fund Z. Now, the question is, we don't know the return of the fund Z, but we want to find the minimum return of the fund Z so that the profit that we get is not lower than that of the problem we solved, the first one that we have seen, so the 2,500. So this is a little more challenging because now how much is invested in the funds is not a variable anymore, but the variable seems to be the return of the new fund. So you have a different variable, different objective, but you can still use this kind of mod file as a baseline. Okay. So what I will do now, I will split you guys in breakout rooms. I will give you, I think now is 11:20, so maybe I can give you up to 11:45. And then we come back to the general meeting room, and then we can share, we can discuss the solution. Do it yourself, discuss in groups. You can organize yourself. Maybe someone is typing and the other are commenting, up to you guys. But I want also that you discuss in your group to find out what is the strategy and so on. So these questions here, this slide, you will find in the file on the website, together with the data run and mod file of the first problem. Okay? So I split you now in the rooms, and then we can come back in like 25 minutes at 11:45. Okay, so how was it? Easy, hard? Any feedback?
So the problem with the second one was that are we still allowed to use variables that are being optimized as part of a constraint?
What do you mean?
Oh, because I'm not sure if we had a bit of confusion in the second problem where we are supposed to minimize the return of Z, but the return of Z is also used in the calculation of the profit. So there was a issue.
Oh yeah, but now, okay. So the problem is different now, right? It's different from the first one. So now, if you look, remember I said that one of the confusion is often between parameters and variables. So if you look at the problem 2, when I tell you that 50% of the capital is in fund X, X is not a variable anymore because you already know that X is equal to 25,000.
Yes.
Right. So the problem is different. I mean, we go through the solution now, but this is exactly to highlight the point that sometimes there is some confusion between variables and parameters. Anyway, let's go to the solutions. Okay. So the first one, we need just to add a constraint, and the constraint is that we cannot invest in Y more than twice what is invested in X. So what we can do is just using a new constraint like that, right? The amount of Y cannot be more than 2 times X. And when we solve the data file is the same. This is the same. I mean, I call these guys T11, T11 mod dot. That's why you see this. And when I run it, I find something like that. Did you find the same?
Yep.
Yeah.
Okay.
Yeah.
So one question for you. Remember that the first solution is 2500, right? When we solve the problem together. Now is a little lower. Do you think is by chance or not that the solution is worse?
No, of course, the first one should be higher
Why?
because we said that intuitively it always made more sense to spend all your money on Y, not X. So if the
Yep.
return for X is lower, then
Yeah, that's right. And in general, every time you have a problem in optimization, like linear integer, these kind of problems, whenever you put new constraints, the quality, the objective function, so the quality of the solution can only become or either stay the same or become worse. Because by putting new constraint, you are removing some of the feasible solution potentially, right? So if you remove the optimal solution, it may be that the new optimal solution is something that was suboptimal before. So by putting new constraints, you would expect to see the problem objective function value at the end of the resolution to be either the same or worse. So this is a point that I wanted to make. So the first one was, I guess, not so hard because it was just a constraint. But what about the second one? So the second one was a little more challenging. And what you have to do here is, as I was saying, understand that first of all, we have a change because now what was a variable is not a variable anymore. Since I tell you that 50% of the capital is in fund X and 50 in fund Z, what does it mean? There is no more fund Y, because if 50 is on fund X and 50 on fund Z, that's 100%. The other thing is that differently from this example, X is not a variable anymore because now I know already before solving the problem, the value of the X and Z. So remember, when you know before solving the problem, the value of something is a parameter. When you know only after solving is a variable. So X and Z are not variable anymore. What is a variable now? Look, we want to minimize, to find the minimum return required for fund X, Z in order to obtain a profit, blah, blah, blah. So what we don't know now is the fund Z return, right? This is the new variable we have. And we already know the return of the fund X. So this is a parameter. So now what happens is that the variable we have to optimize for is the return of the fund Z. And this is also the objective because we want to minimize that. And the new constraint is what? Is that we want to obtain a profit no lower than that of the problem we solved together. So the 2500. Meaning to say that also this now, the allocation doesn't make any sense because now X, Y, Z are parameters. We know that X is 25,000, Z is 25,000 and Y is 0. So we can even remove Y completely. So how can we model that? Now we have the parameter Rx from before. I put two, I mean, if you want to put those as parameter, fine, but it's basically numbers that I will specify in the data file. So how much capital to X is 25,000, right? How much capital to Z is 25,000. And the new variable is the return of the value of the fund Z that we want to minimize, right? And the new constraint is that the total return, that is 25,000 times the return of X, and these two guys we know already, plus 25,000 times the return of Z, that this is now the variable we don't know, must be at least 2,500. Okay, so far? If you have questions, let me know. Data file, okay, so we have the same parameter as before, and now instead of capital 50,000, we have capital X 25, capital Z 25. because the problem tells us already that this is how we split the money. So what we do now, we solve the problem, and then we find out that the objective, that is also the value of the variable, is 5.5%. Did you get the same?
Yeah.
Okay. Anyone got any issue or any questions about this? I mean, I will upload the slides later when like this afternoon probably, or just after the course. But so you will find everything, you can double check. But since we have still like 5 minutes, if you have any question or anything about what we have done today.
I actually have a question.
Yeah.
The data file cannot have any expression, right?
No.
So for example, I wrote capital, and for capital X, it's capital divided by 2. That won't work.
Usually expression, I would say keep separate. So if you have something like that, you can put it in the mod file as a constraint.
Okay.
These kind of things you can also put actually in the RAM file. I didn't say that because I wanted to keep it simple, but in the RAM file, you can also specify some assignment, or like some, let's say, operations between parameters.
Okay. Also,
Okay.
can you mention how to write a default value?
Oh, yeah. You basically here, for example, let's say you want to give a default value to this guy.
Okay.
So you have parameter Rx, comma, then you write default space the value and then semicolon. So I show you what you can do is basically, where is it? Something like that.
Okay. So there is no equal to sign here. All right. Okay.
Not here. Usually the equal, if you have something like that, you have these in the data file, or you can have this kind of stuff in the RAM file.
Okay. No, I actually tried to give a default value with an equal to, and it didn't work. So
Yeah, you will have some syntax error. So AMPL is great, but sometimes when you do something that you think should work, it doesn't, and that's usually because of the syntax, or because what you are doing can be done, but you are doing it in the wrong file. So maybe it must be done in the data file or the RAM file. It happens all the time, so don't worry.
I have a question.
Yeah.
So I was just wondering about the workspace. Basically, in MATLAB, you have one workspace where you borrow all variables from. Similarly, in this program, if you were to write any assignment commands, for example, in the run file, how would we like? Can we take all variable names and then assign values to that, or how does that work exactly?
With parameters, yes. With variable, no, because you have to, I mean, unless you fix the variable, but this is something else. So let's say that, for example, you have a variable and you want to keep it as a variable in your model, but you want to fix that to a specific value. You can do that in the RAM file. There is a command that is called let. Let is when you assign a starting value to a variable, and then fix means now the variable is like a parameter. The value is fixed when you solve the problem. So these are some additional commands that you can use. It's possible. For this first lecture, I didn't want to introduce too many things because I think it's already a lot. But yeah, it's possible. In the RAM file, you can do, even you can have if, for loop, while loop. You can have a lot of things in the RAM file. Does it answer your question?
Yeah, thanks.
You're welcome. Okay, so if there is anything else, we have 2 minutes. Otherwise, just the plan for the next one that will be in 2 days. So the next one will be about, we start to see something about integer programming. And the next one, there will be also something else that is the homework. So I will explain more about that next time. But the structure will be more or less the same. So the first part will be some content, and then we have a pause, and then we have a problem together, and then some questions like that. So exactly the same structure. And the only addition is the homework at the end. So I think that's all from my side. Thank you for joining. If you have any other questions in the meantime, just feel free to write me an email. I will upload the slides and the video when ready on the website of the course. And I will also upload the material for lecture 2 as well in the website of the course. So thank you a lot. I think we are on time. So if someone has the really last question, otherwise I think we can close here. Okay. Oh, thank you. Oh, you're welcome.
Thank you.
Yeah. And
Thank
if
you.
also,
Yeah.
if there is any feedbacks, like if the pace was too fast, too slow, just let me know by email so I can adjust for the next time, because I mean, there is a group, a big group. So I try to do something balanced, but I also need your feedback in case it was not optimal. Let's start to use the optimization keywords. Okay. Great.
Thanks.
So see you next time. Bye-bye.